So yeah, I'll mention you guys don't need any software for any of this stuff tonight. Like honestly, like you need to work on stuff because y'all. I know all of you have homework, all of you have things going on. So like you need to do that in the background. Go crazy. Just don't have to be loud or anything. If you want to take notes, you can do that. But yeah, so I'm going to be teaching intro to control systems. So this, I will say, it will be hard material. This is stuff that like I didn't even touch until like junior year of college. So if you have questions, ask away. I have no problem answering questions, no matter how simple or dumb you might think they are. Control systems are inherently difficult to understand, especially if you are completely new. But what I'm going to try to do is give you guys a kind of cursory exposure to some of this stuff to then, or to a point where you know what you don't know and now can jump into like doing like self-learning stuff online, finding YouTube tutorials, whatever, stuff like that. So, I'm going to get this going. So, yeah. So, kind of what I'll talk about. So, I'll introduce myself. I'll introduce what the heck control systems are. We'll talk a little bit about stability and control. Is there anybody here from C at all? C challenge. 1, 2, 3. Okay. If you guys, did you guys go to like any of the classes like last week for like stability and control or something?
Yes.
So some of that might be familiar already for you guys. For everybody else, I'll try to introduce some of that stuff. Then I'll talk about open loop versus closed loop control. Then I'll talk about block diagrams. And then two main types of control systems that we're going to talk about are bang controllers and PID controllers. Yeah, the name sounds goofy, but that's just what they are. Talk about response characteristics, how to apply some of these things to physical systems, and then some additional resources and stuff. So, as I mentioned earlier, some of this stuff will be difficult. This stuff is naturally hard. For example, this was the first class that I got less than 20% on an exam on once. I've since learned, but the very first time it can be difficult. So don't feel worried at all if you're confused. Just ask away, and I'll be glad to help where I can.
What class is this like related to?
I don't know what it's called specifically here at UAH. I think there might be a class like systems dynamics or something. Like I have a roommate that's taking it. I think it's a junior level class here. I think at my undergrad it was called control systems. Let's see. There's another class here called aircraft stability and control. That's a senior level class that they teach here. It's some of the material might show up in a handful of different classes, but typically you'll start getting exposure to it around junior year-ish, I think. So, yeah, but this is going to be just getting you guys exposed to it, so then like when you're in those classes later on, you'll already kind of know, all right, I know this at least exists. I've seen such and such type of diagram before. You're not going to be just completely like drinking from a fire hose for 4 months and want to bang your head against the wall. Yeah. So, for those of you, if you don't know me already, so I see a few people here that were in the CAD class that I taught a while back. So my name is Ben Campbell. I am a grad student here at UAH. I did an undergrad in mechanical engineering, and here at UAH, I'm doing grad school, unfortunately, but the government's paying for it, so that's cool. My background mainly is on a variety of different spacecraft. So far, I've worked on 6 things that have been delivered to space, and there's a handful more that are either still being developed or awaiting launch. Also within the club, I'm the program manager for spaceflight and Terminus project manager, and also mentor for the RCS challenge. So, what the heck are control systems? So, is this not freezing? Okay. So, everybody here, or is there anybody here that doesn't know what the heck control is? Okay. various sensors on board, you have commands coming from the ground, basically going to the rocket, doing a bunch of math, and then in the end, some of that math outputs to, all right, output such and such thrust at such and such angle, do blah, 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 and it's probably doing it thousands of times a second to then do a nice little and just stuck. So, a lot of complex things, but luckily with something like a microcontroller, a computer, different stuff like that, you can trick little pieces of wire into thinking really, really fast and do a lot of math really, really quickly. So,
An estimate of the tilt and angular velocity of the cubely, and the Hall sensors provide the angular velocity of the reaction wheels.
Let me try something really quick.
Based on these estimates, a nonlinear controller is used to balance the cubely on its corner, while the angular
Is that Let's see. So this is actually a little cube that what it does is it can balance itself perfectly. It can also walk and it can stand. So you can have it stand right on a corner, you can have it right on an edge or something. And so no strings, no magnets, no anything goofy. How this is standing up is that it's literally just got little wheels on the inside that spin in a certain direction and apply a torque to keep it from falling over. It's kind of similar to like if you've ever like kind of leaned back in your chair and you're trying to lean on the very back two legs and you kind of do that a little bit to try to save balance. It's doing the equivalent of that but with these wheels. So we don't have to watch this whole thing, but it's just it's balancing. It's got control systems on board that basically what it has is it has sensors basically telling, all right, here is where gravity is. Here's kind of the general direction of it. Here's what down is. I'm tracking my motion where it's kind of wobbling, and then really quickly making these corrective maneuvers with these little wheels to say, all right, I want to be in such and such orientation, and then go and just kind of really gently balance. Do you have a question?
So, is that like the reaction wheels thing in Kerbal Space Program?
Yes, actually. So this is exactly what reaction wheels do. So this is just a little goofy demo just showing you can make a little cube walk, but it's the exact same principle for reaction wheels. So basically you have one thing spin one direction, the rest of the spacecraft goes the other direction. So you have these actually really, really precisely go and try to, line things up and orient them. And so some of the stuff that I've worked on in the past has actually been specifically making reaction wheels kind of like that for like a CubeSat. So yeah. Lots of cool things. So basically they can be used to define any kind of behavior in a system. So this will be done with various devices, typically all operating in different loops. These loops can be really, really simple, or they can also be really, really complex. Some simple loop, for example, would be like something like a thermostat. It's like just sitting, looking at the temperature of a room, turns on a heater or an air conditioner or something. Or something really complex like a rocket engine. And I'll talk a little bit about that later. Typically, they are used to get some system to a desired state, whether that be some sort of position or velocity, acceleration. Pretty much anything that you can put a number to, you can make a control system trying to have your system target that value. So control systems rely on a few basic things. You've got basically your inputs. These can be in the form of like commands. They also can be in the form of disturbances. So for example, if you have a rocket, it's coming and descending down through the atmosphere to land on a pad, there's probably going to be wind gusts here and there. How are you going to react where if you're falling straight vertically down, but then all of a sudden some wind gust goes and just blows across the side? You need to somehow be able to account for that and correct for it. That's some sort of an input. And an output is typically going to be how your system responds to that. So like a rocket, if it's coming and landing down, if a gust of wind blows over, it's going to have some math on board that basically says, all right, I've deviated a little bit from the side, and then I'm going to correct and have these engines gimbal a little bit to kind of get me back in line, back on the needed trajectory to get to the ground. And then systems are what kind of combine these things together. So you have one thing come in one side, something else comes out the other end. So oftentimes these are called processes or plants if you're talking to like a control systems engineer. Also, these incorporate feedback systems, and I'll talk a little bit about those later. It is important to have all of your potential inputs and outputs properly defined, because if you leave certain things out, you can, you're going to be putting your system out in the environment, but then something can go wrong and you're not going to be able to correct for it. For example, if you have a rocket and you have some code that's saying, all right, this is the landing trajectory that I need to do and all the maneuvers to get there. If you don't account for wind, you're going to go way off, the rocket's going to blow up, it's going to be a bad day. So, one example, cats are designed to live in gravity.
When an animal is suddenly placed in a weightless state.
But if you put them in microgravity, they don't like it. It's not good.
Will invariably rotate their bodies longitudinally in midair and land on their feet. This automatic reflex action is almost completely lost under weightlessness.
So, cats have their own basically biological control system that tells them, all right, here's my orientation. If I'm falling, here's how I kind of jerk myself around to land on my feet. But cats did not develop to live in microgravity. So then if they're put in that kind of environment, they have no idea what to do, and you kind of saw them jerking around a little bit. So make sure you have all your possible inputs that could happen at least accounted for in your code, so that type of behavior doesn't happen to your payload. So control systems, they are also everywhere. Pretty much anything in our modern lives has a control system in it. You yourself are a control system. You are one of the most advanced control systems that has ever existed. Like every biological system in your body, like your heart rate, you've got your brain, you've got your lungs, you've got everything is a control system somewhere. So, also a toilet. A toilet is also a control system technically. We'll talk about that later. Obviously, a rocket engine also has control systems in it. Does anybody else, or anybody think of pretty much anything, and I can try to think of a control system associated with it? A table. A tape, or got me there. Anything of any level of complexity, like any kind of like
Folding table.
IKEA table.
so. Maybe something a little bit more advanced, maybe. Life is the most complicated one of all. So like, if you start running, for example, you're gonna be exerting a lot more energy, you're putting a lot more effort into it. Your body's gonna know to just, all right, I need to increase my heart rate, start increasing blood pressure, doing whatever. It's also gonna start doing thermal regulation. It says, all right, I'm so hot, I need to cool down. I'm gonna start sweating. I'm gonna do something like that. Anything else between like a table and a living thing? Any other ideas of something?
Fridge.
A fridge. Yes, that's an excellent example. So, say you make leftovers. You make a big bowl of pasta, but you live by yourself, and so you've got one little bowl for yourself, and you've got like 6 little Tupperware containers left of pasta that need to go in. They're all going to be hot. They go in. That's going to naturally kind of increase the ambient temperature inside the fridge. The fridge will be able to record that temperature change and be like, all right, I need to increase the circulation of the coolant, start cooling things down, and suck that hot energy out. But yeah, pretty much anything of any level of complexity has some sort of a control system associated with it. These can be a variety. They can take a variety of different forms. You can have like electrical, mechanical. You can have fluid systems, software, thermal. There's a whole bunch. If you look back in like kind of the history of like really, really early computers, a lot of them were actually made to basically be analogs of other systems in the real world. I'll talk a little bit about those later. Also, a lot of the math kind of governing the control system side of a bunch of these systems, you can actually make, for example, there's one type of common mechanical system called like a spring mass damper. You can actually have that type of system represented in the form of a circuit, and it'll output the exact same type of behavior, but instead of looking at like the forces or acceleration on something, you're looking at the voltage on something. And so you can actually simulate a lot of these very, very complex things without needing to build a whole mock-up of something. You can instead just kind of build a little circuit and observe the exact same behavior. And I'll talk a little bit about that later. So stability and control. So stability is basically the ability for a system to kind of just naturally correct for disturbances and conditions that act on it. For example, a plane, it's kind of naturally kind of flying fairly level, and if a wind gust happens, it doesn't just make it fall to the ground. Typically, it'll kind of bulge a little bit to the side, and then it'll kind of level out later. Oftentimes, that's called static stability. For kind of more complex things, you'll also have like dynamic stability. So that's like, typically there's like control surfaces on a plane that help you correct for wind gusts or doing certain maneuvers and things. Control is it's typically associated with dynamic stability. One example of like static stability, like really easy, is like if I'm sitting in a chair. If I am here, I don't have to think about like moving my muscles to stay up. Like if I just go completely limp or something, like I'm in the chair, I'm stable, I don't have to do anything. But if I am standing, I'm not gonna just flop over, but I have to kind of in the back of my head, I'm thinking, all right, I have to kind of stay balanced. You do it after a while and it just comes automatically, but really your brain is thinking. And if you, does anybody here use like, or try like the Wii Fit board, or like little Wii balance board thing? There's like that one balance test thing where it's like, all right, test your balance. And like you would expect, like you're standing there and you're gonna have like, perfectly rock solid stuff. But really, what your body's actually doing, there's these tiny little micro corrections that it's doing with your toes and the balls of your feet that you can actually see and like record them with this little balance board that's like detecting all the little differences that are happening. But your body is able to like stay within a general bound that your body notices as balanced, but the little Wii board can tell all those tiny little differences that are happening. Actually, no, I don't want to exit OBS. Let's see. There we go. There we go. So, here's kind of a little, and this narrator talks so slow, so I'm going to speed up the voiceover just slightly.
A stable aeroplane is easier for the pilot to control. An unstable aeroplane moves further away from its intended attitude when disturbed by turbulence. In this video, you will learn about the different types of stability. We'll use longitudinal stability as an example. It relates to the pitching plane, but these terms apply to other axes as well. When disturbed by a gust of wind, positive static stability is the initial tendency of the aeroplane to return to its original attitude. Most training aeroplanes are designed this way. Neutral static stability is the initial tendency of the aeroplane to continue in its new attitude. Negative static stability is the initial tendency of the aeroplane to move further and further away from its original attitude. This is not desirable, so most aeroplanes are not designed this way. Whereas static stability describes the initial tendency of the aeroplane to return to its original attitude, dynamic stability describes the time and how many oscillations it takes to get there. When disturbed by a gust of wind, positive dynamic stability is the tendency of the aeroplane to return to its original attitude after a number of decreasing oscillations. The aeroplane's nose pitches beyond its original attitude in each oscillation, but decreases in amplitude until it settles. Neutral dynamic stability is the tendency of the aeroplane to continue to oscillate without settling down. Negative dynamic stability is the tendency of the aeroplane to continue to oscillate with an increasing amplitude.
So very bad.
This is not desirable, so aeroplanes are not designed this way. Most aeroplanes are designed with stability in mind. Some aeroplanes are made to be unstable. We'll discuss how, why, and the features that make it so in another video.
I think that's it, yeah. So, I will say it is possible to make things that are like inherently unstable and then just super overcompensate with really advanced control systems. So, for example, this plane, you can't tell, its wings are backwards from what are expected for a normal plane. But it is actually impossible to fly with just like, a human operator saying like, all right, just kind of pitch up, pitch down, do these things like doing those manually. What it's really doing is the pilot on the inside, they're commanding, all right, I'm going to go up or go down or, bank one side or another. But then those inputs go through a whole ugly, complicated control system that then looks at all the sensors where it's like, this thing is actively trying to rip itself apart and slam into the ground, but I want to get to such and such orientation and position, and it does things. So it is possible. I do not recommend it for 2 month, especially for like if this is any of you guys' first experience building anything. Yeah. So now I'm going to talk about open loop versus closed loop control. You're going to learn why closed loop control is good and open loop control is horrible. So for this, I need one volunteer. Come on, or saw Kyle up, or yeah, Kyle, you can come up.
Okay.
There'll be a second demo in a bit, so you can come up next. All right. So what I'm gonna have you do actually first, I'm gonna have you here. I'm gonna stand you kind of right here, and then can you put your glasses down just on the table? So what I'm gonna have you do is, so here I'm gonna have you face this direction, face towards this wall. And so I'm gonna back just a bit. So now what I'm gonna ask you to do, just cover up your eyes, close your eyes and everything, and then just spin around until I tell you to stop. Yep. Yep.
Oh, I thought you meant like yep. Like
No,
stop.
just keep spinning. And so what I'll do is when I say stop, I'm gonna ask you to basically try to finish as close of finish as close as you can to be in the exact same position that you started at.
Okay.
Stop. Do you think you're in? Yep. Just kind of move around until you think you're good.
Okay. And good enough.
All right. Open. All right. So do you see what went wrong here? He's not in the same orientation like facing the wall as before. So now with your eyes open, go ahead and spin. Or you can put your glasses on.
Okay, I'll face this way for
Yep.
the purpose of demonstrating.
So now, spin again, and then when I tell you stop, then orient yourself towards the wall. And stop. So now you can see he corrected for it. So it's a little bit easier. So, let's see. We'll do another example now. So, are you still up? Or Kyle, actually 2 people for this one. Alright. So this one you won't have to move at all. This time you're gonna be a smart guy. So what you're gonna do is I'm gonna have you actually let's have you stand right here. And then Kyle, you can move wherever you want. So what I'm gonna have you do is I'm gonna have you close your eyes. So now what I have a marker in my hand. Now what I want you to do, so keep your eyes closed. Yep. So now what I want you to do is grab the marker from my hand. It's right out in front of you. There you go. Alright, so now you can open it. So now you've got the marker. So then now, what I'm gonna have you do, no, not quite. So, what I'm gonna have you do, we're gonna do the same thing, but this time, Kyle, I'm gonna have you come over here really quick. So you're gonna keep your eyes closed. You're gonna give basically verbal commands, trying to help
shift
him.
this way. I'll stand on that side so everyone can see.
Sure. Yeah. So here I'll have you shift inside just a bit. All right. So now, similar deal. You're gonna try to grab it, but Kyle is gonna give you auditory commands trying to help.
Oh no. Okay. Move your hand forward until I tell you to stop. Stop. Now move your hand to the left until I tell you to stop. Stop. Okay, move it forward left a little bit more. Stop. Yeah.
open your eyes. So now try to grab it from my hand. There you go, a lot quicker. All right, so does everybody kind of see, you know, some ways are a little bit easier, some are a little bit harder. Can anybody tell me why? Thank you guys. Can any of you guys tell me why certain things were easier versus harder? Anybody?
You had a point of reference.
Mm-hmm. You had a point of reference. Anything else? Or let's see, in the gray and then in the black. Or yeah. Mm. Yeah.
There's a shorter I guess time from thought of idea of where it could be to action of trying to get there, I guess.
A little bit.
The sense of sight is our most, I guess, accurate and precise sense.
Mm-hmm. So that is the eyes and the ears also are different ways of basically getting in input. Basically, what I'm getting at here is that those different situations rely on either incorporating or ignoring feedback. Feedback is basically where we are able to see something, we see something that is wrong with it. For example, we have the marker right here, and I have my hand right here. I want my hand to be here, but I can see or be told that my hand is, you know, some distance away from it, and I can see that while I need to take my hand and move it, you know, up a little bit, to the side a little bit, move it forward, and then connect with it. But if I have, if I'm blind and I can't see it, I'm just kind of wandering aimlessly. I can have a general guess where it's like I'm somewhere around here, but you know, having your eyes, that's like one of the best ways that you can just see that something is different. You want to close the gap on something. So open loop control is basically the equivalent of doing something while you're blind. You basically have like a general guess at what you're trying to get at. For example, like if you're trying to walk in a straight line, like you can do that. You can do that with your eyes closed. You can kind of walk in a straight line. It's not the end of the world. You might veer a little bit, kind of one side or another, but you can generally walk in a straight line. But closed loop control, you incorporate feedback. You can see, all right, I need to adjust a little bit to the side. I need to do something. For example, if you wanted to walk across campus, you're not going to do that with your eyes closed. You're going to have your eyes open. You're going to watch out for some idiot on a one wheel coming up behind you on the sidewalk about to run you over or something. So, when possible, closed loop design with feedback should always be considered. You should always try to incorporate that if you can. Sometimes where if you have just a really simple task, something like walk in a straight line, you can get away with an open loop controller for some of that stuff, but still, as best as you can, it's always a good option to try to do a closed loop design. And so the reason why this is called open and closed loop is because it has to do with kind of the flow of information with how these control systems operate. So an open loop system basically have something come in, you go through some controller, you in this case trying to grab a marker out of the air, I have an input that's from my eyes, goes through a controller like my brain, then that control signal then goes to a process which is my brain telling my arm to move in a certain way, and then the output is eventually my arm is in some position. But a closed loop system, you actually are able to feed it back in on itself, and you follow the similar process on the top part, but you have this, on here they call it just like a measuring element. This is just your feedback loop. This is something where, you have the marker here, your hand is here, and that little measuring element is kind of, your eyes are able to see, all right, my hand's about a foot away at such and such angle, now I just need to feed that information back in to my controller, and then, eventually I can move my hand over and intercept with that marker. Let's see. So, let's see. one kind of exercise we can do here now. Let's think of how we would make a closed loop controller for a system doing just something nice and simple. We just have a tank, we're trying to fill it up with liquid. There's some different options. You can have like a scale underneath the tank where you're just kind of filling it up, and you're going to get an increase in weight as it goes up. You can have some sort of a pressure sensor. You have some different things in there. If you want to have like a bunch of crickets in the tank and then pour enough liquid in it, they're all going to drown and they're going to stop chirping. That is one way that you can measure something. I don't remember what the exact situation was, but like there was something like long ago that was actually something people did. Any other ideas of ways that you can, fill a tank up with liquid up to a certain level and tell you when to stop? Any other ideas?
A float switch.
Or was that?
A float switch.
A float switch.
Same thing, a buoy.
Yep. So you guys are right on the money, dude. So one thing that I want to make sure you guys are also aware of is there's a lot of different options for how these control systems can be made, but it's also important to remember the application. What are the requirements needed for what the thing is supposed to do? So I've got a video. Does everybody know what the inside of a toilet looks like how it works? Does anybody not know? Alright, cool. I won't play the video then, but you can see. Alright. So those diagrams I had on that other slide with the kind of the straight thing, like it's not closing a loop, it's an open loop, versus a closed loop, it's making a full circle. Those are examples of block diagrams. So when you have really complex systems, it can be really helpful to try to take these things and condense them down into smaller, discrete tasks. But then eventually, all of those things get combined together into some complicated behavior. So for an example, the human body is one of the most complex control systems there are. You don't have to sit there and if you're trying to scoop sand out of the ground, you don't have to think, all right, I have this finger, I need to move such and such muscle fibers certain way to get to some curl. Do that with all of them, and I do, I try to get my joints all to these angles and try to do whatever. We don't have to manually think about each little thing, because God just kind of snapped his fingers and is like, all right, that's how it's going to be. That's cool. But unfortunately, us poor humans, if we want to do anything similar, we have to make all of that stuff from scratch. So there's a lot of complicated behavior. Like for example, have any of you guys seen the big robotic arm on the Astro rover? So there's a lot of, or has anybody here not seen it? All right, good. So, if you're trying to control that thing, it's not like you can just tell it to go, all right, I'm gonna go write some cursive word or something, you're doing all these fancy strokes, getting all these fancy angles and everything. It is possible to make it do that, but it's really, really complicated. You have to break things down into, all right, I have such and such joint at such and such angle, something else at some other thing, doing blah, 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 blah. It's a lot of complex behavior that it can be helpful to break it down into a series of more simple steps. So you can either have a human that's doing things just automatically, or you can make some machine that does various scooping. If you get that reference, you're cool. For example, think of a rocket engine. Who here is anybody here not played Kerbal Space Program? Alright, a few people. So if you haven't played it, just get it. Just play it. Get the first one, wait on the second one, but basically you make rockets, you design them, you fly them. It's just a fun game. But when you're flying a rocket in Kerbal Space Program, those of you that have played it, you're not sitting there trying to think of every little system all the time. Typically, if you just have a rocket you're going up and you're launching, for the most part, you're just kind of thinking about general thrust, kind of orientation, and kind of the angle that you're flying at. You're not sitting there trying to think of, all right, such and such pump is at such and such pressure. I need to turn this little thing over here, turn a knob, flip a switch, do all this other stuff. Really, you have some sort of simple command that you want imparted onto the system, and in order for this engine to actually execute that behavior that to a human sounds nice and easy, it's just angle an engine a certain way and put a certain amount of fuel in it. there is so many other processes that have to happen between you just kind of flipping a couple switches and then it actually actuating and doing all of this stuff. So you have some inputs, it goes through a nightmare of controls magic, and then comes out to some desired output in the end. So block diagrams can help you think of these really complicated systems, or you can break them all into these separate tasks and then combine them all into some unified behavior. For example, you can have some sort of equation that has thousands upon thousands of inputs to it, but you have just a few things defined at the beginning, goes through some ugly equation, and then at the end, you just have thrust and direction. So, if any of you don't know what the RS-25 is, it is the engine used on the space shuttle and also the core stage of SOS, one of the biggest, most powerful rocket engines ever made. Here's kind of a gimbal test over at a test stand. So it's just testing, it's fired up, and it's doing these tests, angling and moving around. You can see all the complex stuff up at the top end. It's kind of a blurry video because it's a little older, but very, very complicated machine. I have no idea the money figures on that test, but probably on the order of at least a few $1 million just to run for a few seconds, because all of this stuff is just stupid expensive and there's a lot of people. But really complicated behaviors that need to be determined somehow. And so you don't want to just go in having no idea how this thing is going to perform. You're going to want to do a bunch of prep. You're going to want to do a bunch of math to try to determine, all right, we're comfortable enough where if we put this thing on a test stand and try to have it gimbal around, we're pretty sure it's not going to explode. So block diagrams and the math associated with them can help you determine what that behavior will look like before you actually build the thing and test it. So this is an example of a block diagram. So this is a closed loop diagram. You can kind of see.
Thanks, pal.
No problem. So you can have kind of these different behaviors all here. So we've got these different blocks right here. These are all kind of just different processes. We have these arrows going everywhere. We have this weird circle with an X in it. I'll explain what all these are. But these are all basically independent parts that can eventually be combined together to define some sort of relation between an input in one side and then an output on the other side. So these block diagrams are composed of just a few basic parts. You've got your signals, which like before we were like, you've got your input and your output, but you also have all of the little connections that happen between any of these different activities. So think of these like, for example, if I'm controlling the speed of a motor or something, I have like some function here, like it just says like R of S and then C of S, like just forget those mean anything, just imagine them as some function. So I can have it like, I have a motor, I want to have that go at a certain speed. It's, some position as a function of time, basically. That can be one thing. So I can just have like f of t, basically, some function of time. And then like C of S, I could have that be, say, like the voltage or the power going to the motor. Some other thing as a function of time. If you see this S right here, that's because of a magic little thing called the Laplace transform that I will not talk about right now, but you can equate things kind of similar. You also have your systems. These are basically each of those little blocks. These are typically anytime you're doing some sort of math or transformation between one type of thing to another. For example, like if you have, let's say you have some sort of setup where you have a potentiometer. Does anybody not know what a potentiometer is? All right. So have any of you ever like at some sort of control panel, or actually your radio, any kind of volume knob, basically. So a potentiometer is basically what that knob is. What it is that you take it, you rotate it a certain way, and then behind the panel, what it's actually doing is that it's basically a variable resistor. So what it basically has is that it has this kind of resistive coil going around, and what it is that as you rotate that knob, it's actually moving a contact and changing the resistance of that little area, which then you can use as an input to some microcontroller or something. Question?
Is that why some of like the AC knobs and cars sometimes get a little warm?
It can be. There is, like, it depends on what they're made of and what it's being used for, but resistors do, like, when power is going through resistors, they do get warm. But you can have, like, some system where you have, like, you're turning, like, the math for, like, alright, I have the math for, I'm turning a knob a certain angle, that's then translating then to some resistance. So it's like, I have, say, from 0 to 180 degrees that I can rotate, that's then changing the resistance value, let's say, from either 0 ohms to 10,000 ohms or something. That would be some sort of like multiplication type operation, for example. You can do pretty much any kind of math operation you want to do other than like addition and subtraction with those. You can do integrals, you can do derivatives, you can do a bunch of different things. Typically, you're going to be looking at like turning some sort of position into, you know, you're breaking it into like its differential components, your integral components, like, you know, those kind of general equations like in physics 1 probably, or physics A, I don't know what you guys call it here at UH, but like you have, what was that?
Torture?
Is that with Cronus? Yes, yeah. But you know how you can have a function of like position, and then you can do like integrals and derivatives to then transfer between also like you're going like function of velocity, function of acceleration, stuff like that. Does that ring a bell with anybody? So that's typically what a lot of that stuff is used for. You also have this thing called a summing junction. This is kind of a bigger one, but like basically just think of it as addition and subtraction. That's all it is. You have some signals coming in and you just have these little symbols by it. So like here we've got like a little plus button or a plus symbol. We have another one here and we have a minus right here. So if we look at this, we have like R1 with a plus sign, R2 with a plus sign, and then R3 with a negative sign. Basically the output of this summing junction is just the sum of these things. So we have R1, like positive R1, plus R2, and then we have minus R3. That is all it is. It might look more complicated. It really is that easy. So what that's typically used for is, that's typically how you tell the difference between something. That is how, like, so if I go to, or yeah, if I go back a slide, so if I have some system coming in here and I'm doing that little like hand grabbing a marker example, I've got this going here, I've got like, I have my desired input, which is the marker's position. It's going through my brain, moving my hand over here, and then I'm feeding back, I'm thinking about it. But then what this feedback loop is doing is, this is my brain basically identifying that, I'm gonna use an eraser now since somebody stole the marker. But I've got the eraser here, I have my hand here, but I can observe that my hand is here, but my desired position is here. I can see that there's a difference between the two. I can equate that, or I can define that either as like a position, like I can either like do the distance, or I can do like an angle, however I want to define it for my system. So that difference that I'm noticing between my hands is what basically comes out of here. So I have the marker's position here, I have my hand's true position here, I see a difference, and then that difference is what goes into my brain and tells me, all right, I need to do something about that gap to close it. I go through, move my hand, and then eventually I have this loop going over thousands of times a second in my brain to where then it looks nice and smooth and I just do that.
Wait, so why do they have plus and a minus?
Plus and minus. Oh, so this is just a general, just some basic layout. This could be a plus or a minus, depends on just however you want it to be. So it would be, everything will be either a plus or a minus. It won't be both. So you can have multiple things coming in that are like, for example, you can have multiple things coming in where it's like a plus here, and a minus there. Or I can have like 30 things going into it if I really wanted to. I have never seen anything like in the real world, go above 3. And really, most of the time, I've only seen, I think, like 1 or 2 things that ever incorporate like 3, or like anything that incorporates more than 2. Anything with like 3, typically, I've seen that as like a homework problem and nothing more. It's for the most part, the only time I ever see that is basically just I have a plus for the desired position that I want to be at, and then I have a minus right here for where like my hand is currently at. And the reason why that's a minus, I'll talk a little bit about that. Like there's some math and codes that I'll talk about. Does that answer your question? So, and then this thing right here, pickoff point, basically that's just saying you can have a signal and it can branch into multiple things if you want. So if you want the same signal going to multiple things at once, you can do that and it won't change. It's nothing too crazy. So you can have block diagrams that get, you can have something kind of more complicated like this, and then what you can actually start doing is you can use those, and since each one of these things will eventually be able to be defined as some sort of an equation, you can then simplify these things. You can start saying, so for example, whatever signal I'm bringing in here, let's say I multiply it by 2, and then here I like divide it by 4. I could then just combine both of those things where it's I multiply by 2, divided by 4. Eventually my block over here would be the equivalent of just dividing by 2. Just multiplying by 2 times dividing it by 4, basically. So that would just leave with, dividing it by 2. Similar deal on the bottom. Whatever you have kind of in line, just treat it like multiplication. They're all kind of in line with each other. Eventually, you can do. There's a certain type of operation where eventually you boil things down to some basic type of loop like this. So you can have this big old ugly thing that might have summing junctions and all these different areas, all these blocks and everything. Eventually, you'll get left with this kind of intermediate section that comes into this kind of form. You basically have something on the top coming straight out of your summing junction. You have some output signal that it doesn't have to be the whole system output. It could just go into another summing junction loop or something. But you have some part keep going, then another part comes down, goes through some other process and feeds into here. I won't go into the math theory behind why this eventually simplifies to this. Just trust me on it. If you want to look into it yourself, just look up like control system, block diagram, simplification, or minimization or something. You'll find a load of resources on that online. If I were to talk about that for this class, that would take forever, and I do not want to. But just trust me on it. This is directly from a control systems textbook I did that I used in my undergrad. So everything you can have some ugly, complicated thing, and it doesn't have to be just this general shape. You can have something that is like whatever the crap this thing is. I have no idea if it's even useful in the real world, whatever it is. But you have something ugly, and then eventually, over time, you can start simplifying it, and then eventually, in the end, you'll be left with, depending on how you define all of your equations for things, you can eventually have, all right, I have some input, go through some vomit of an equation, and have something useful in the end. That can help you start to simplify a lot of very complex behaviors fairly easily. You can kind of think of it also like, how in Excel, you can have different functions and cells reference each other and all these things. You can spend a bunch of time, deriving some equation all by hand, and you have some ugly equation where it's like change a value in one cell and it does some math and spits something else. Or sometimes it can be easier to break it into multiple steps where it's like, all right, one cell has one equation, that gets referenced by another one, it does another step of math, it's a little bit easier to chew. Do that a series of times and they all kind of feed into each other. Very similar to that, so it's a lot easier. Also, all of this behavior can be simulated in a software environment. Highly recommend you try that. You're probably going to have to if you use control system stuff. Bless you. has anybody here not touched MATLAB yet with any of their stuff? Alright, a few people. So, consider yourselves lucky. It's not that bad, but yeah, in MATLAB there's an environment in MATLAB called Simulink. Simulink is very helpful for a bunch of this stuff, where they make control systems as easy as literally just dragging and dropping boxes and arrows, and then you basically give some function at the start that you can define. However, you can have like a step function where it's literally just something turns on, or you can put in some ramp, you can put in whatever equation for an input you want, and then you can literally just, there's like a little button or a little box you can drop in that looks like a meter, some sort of chart that then just says, all right, here's what this whole thing spits out in the end. You can see all the little curves, you can see the behaviors and all this stuff. And so, I'd recommend checking that out. Also, all of these equations, chances are you can write a lot of this in, like, I'm guessing most people in here for like software are using like the Arduino IDE or VS Code or something, some sort of C-based, like C/C++, whatever stupid variant you want to call it, whatever you're using for that to control your system. All of these functions can very simply be executed in that. Yes.
I thought I heard there was a Python for the Raspberry Pi.
For Python you can do this stuff as well. Pretty much any programming language that you can think of, you can do control systems in it. But like, you don't want to make this in Java, for example. That just be why. But like C++, was that?
I've done so much PID in Java.
My condolences.
I can share the website with you that like I just copied everything from.
Okay. But yeah, like C++, Python, or any of the variants of those, like, what was that?
Linux.
Yeah. So yeah, you can replicate all this stuff, and I'll show you guys how to do that in a little bit. So now I'm going to talk a little bit about different types of controllers. So first one, the easiest one that you will ever hear of, is a bang bang controller. This is basically turns things on or turns things off, or turns things one direction or the other way. It's literally called a bang bang controller because if you think of yourself kind of in a car, if it was controlled by like a bang bang controller, it's like, all right, oh, I'm veering a little bit to the side, I'm just gonna veer to the right, and then oh, I'm a bit too far to the right, I'm gonna just turn to the left, and you just kind of bang side to side. A real world example of this is something like a thermostat. You have some sort of sensor in the room, some sort of thermometer that looks at the temperature of the room. It will see, all right, I want to be at some temperature, let's just say 79 degrees, or actually 69 degrees, because the funny number. So if we detect, okay, we've gotten to 70 degrees, it's like, all right, turn on the air conditioner until we get to 69 degrees. Or if we're at 68 degrees, then it's like, all right, turn on the heater, bump up to 69 degrees or something. One thing to keep in mind though, this doesn't control the speed at which something like activates or turns on. It's like, it's not saying the heater is going to draw such and such power. Like, it's just saying, all right, it's on or it's off. That's basically what it's doing. So very, very simple. For example, who here is in the RCS challenge? Few people. So at least for some of your guys' early tests, I would recommend trying like a bang bang controller, like with the RCS thrusters, trying to rotate. Just something basic at first, just to prove that it works. And then eventually adapt to PID control after, or something else. But PID, or like a bang bang controller, could just be useful, like proof of concept stuff, just to at least get you moving. So this is just like a little example. So has anybody here been to like the either Autotopia or Autopia ride at Disneyland or Disney World? All right. Well, it's kind of this older ride, if you can't tell. It's from like the early days, but it's basically like you're on these little cars. You can kind of see they kind of bang on the sides. You can kind of steer them a little bit, but if you just let the hand off the wheel, they'll just kind of naturally guide themselves on these little tracks on the ground. You just kind of bang against the side, bang against the other side as you make a turn in the other way. But yeah, you can kind of see the little track it's on. It's a little on the side, kind of just veers around, but yeah, you can see. And here's a little video talking about controlling a car with like a bang bang.
Technology being developed for driverless vehicles is pretty incredible. In the near future, there will be robotic cars traveling on normal roads with the safety and efficiency of the best human drivers. These autonomous vehicles use various sensors to be able to localize themselves in any environment. They are also then able to construct a detailed plan to get from their current location to any desired destination. This video will provide an introduction to how these autonomous vehicles are then able to follow their desired trajectories. Getting a vehicle to follow a trajectory may seem simple to those who have driven before, but is it? Let's take a deeper look at this in a lab setting. If we want to follow a line, but we are too far to the left, we turn to the right, and vice versa. But how much do we turn? If the steering wheel is turned a fixed amount to the left or to the right, the approach is called bang-bang control. For controlling a car, this doesn't actually work that well. The response is very jerky and uncomfortable for the passengers. Fortunately, we don't have to steer like this in it.
So we'll watch more of this video a little bit later. But you can kind of see it's kind of jerky, bangs you around. So a little bit better control system that can be a little bit more complex is a PID controller. There's also, you can have PD controllers, you can have PI controllers, you can have just PI, like you can have any combination of these. You can have any single one of these things, or all three, or any two of them, whatever you want. But basically PID controllers, they basically all revolve around utilizing behaviors that it can be defined as either a proportional component, an integral component, or a derivative component. Basically what they mean is, and you see the word error over here. This error is defined as basically what is the difference between, my desired position and my current position. If you saw in some of the block diagrams earlier, whatever the signal coming out of that summing junction was that combines the current position with, or the desired position with the current position, the signal that comes right out of that is called error. Error is basically just, how off are we one way or another? What's the resultant angle that we need to move? What's the distance we need to move? What's the speed we need to move? The temperature, the pressure, whatever system it is. How off are we from where we are desiring to be? So that error can be, you can basically have a kind of time log of error over time where you can look at, all right, 1 second to go, let's see, if I start at like time 0, I want to have my hand go to this eraser. At time 0, let's say I'm here. So I have about 2 feet or so of error. 1 second later, I can be here and it's like, all right, now I'm 1 foot of error. Now I'm a little bit closer and I can change how I'm approaching it a little bit better. And so you can have kind of a time log of that, and what you can do is you can have integral and derivative components taken, where basically the integral component, think of that as accumulated error over time. Think of if I have a rocket and I'm like trying to land and the wind just keeps blowing, that's going to kind of just accumulate some error over time. If I'm having that descend over the course of like 5 minutes, it's just kind of just accumulate, and I need to account for that. Similarly, I can also do the derivative of the error. So that's going to be how fast am I changing the error. Question?
Would you like a driver's timer?
Sure, you can chuck it. Oh, jeez.
You almost owed me a laptop screen, bro.
Everything good?
Yeah.
Okay. So like the derivative component, if I have a rocket, I'm descending down or something, I can look at like, let's say my finger is where I need to be and the rocket is off a little bit. I can either have a really slow gradual change, or I can have a really fast change. you can kind of tell certain speeds of behaviors or responses are better than others. Like if you want to be really jerky and move to the side, or just kind of gradually go over. So the derivative of the error can also be important. And I know I'm talking about these things just with text right here. It sounds kind of abstract. That video that we watched just a second ago, it'll visualize all of these things for all these different components. So each of these components, they can each be multiplied by their own gains. They can be summed together. They can do whatever. They can each have their own little chunk of one of these closed loop block diagrams. So
Said, if we want to follow a line, but we are too far to the left, we turn to the
a
right.
few seconds
and vice
behind
versa.
that.
But how much do
So-
we turn? If the steering wheel is turned a fixed amount to the left or to the right, the approach is called bang bang control. For controlling a car, this doesn't actually work that well. The response is very jerky and uncomfortable for the passengers. Fortunately, we don't have to steer like this in a car, since there is a range of angles the steering wheel can take. One way to set the steering wheel angle is to use what is called proportional control. Rather than turn the wheel a fixed amount, proportional control steers harder the further away we are from the desired trajectory. We take a measurement called cross-track error to define how far away from the desired trajectory the vehicle is. Therefore, the steering angle we use is this cross-track error multiplied by a scaling factor called the proportional gain. The range of values the proportional gain can take drastically alters the performance of the vehicle. As you can see from this overlay, the performance gets better as the gain increases, but at a cost. If you start too far away from the desired trajectory with a high gain, the system can spin out of control. With the best gains, proportional control returns better results than bang bang control, but it still doesn't work that well. With proportional control, the car can be crooked when it reaches the center line. The result of this is that the controller will repeatedly overshoot the actual desired trajectory and not actually follow it. To correct this overshooting problem, we need to consider additional error measurements and use them to update our steering command. A good candidate for an extra measurement is to look at the cross-track error rate, or in other words, how fast we are moving in a perpendicular direction with respect to the desired trajectory. If we are perfectly following the trajectory, our cross-track error rate will be 0.
So this is that derivative term, basically.
This rate term can then be multiplied by its own gain and added to the proportional term to construct an updated controller. Now that we have two terms, we have two gains that must be tuned simultaneously. Conceptually, we can think that increasing the proportional gain will increase the pull that the vehicle feels towards the desired trajectory. Increasing the derivative gain increases the resistance the car will feel against moving too quickly towards the line. Fixing the proportional gain, if the derivative gain is too low, the system will be what is called underdamped and it will still oscillate. If the derivative gain is too high, the system will be what is called overdamped and will take a long time to correct for offsets. Properly choosing the derivative gain allows the car to approach the desired trajectory quickly with a cross-track error rate close to 0. This is called being critically damped. Despite the success so far, for a complete controller, we're not done yet. Environmental factors or mechanical defects can change the vehicle's nominal behavior and thus the performance of the controller. For example, if there's a heavy crosswind, the vehicle will drift unless the driver counteracts this wind force with a corrective steering command. Here is an example we can easily demonstrate. Imagine our vehicle is driving along and hits a pile of rocks, which knocks its front end out of alignment, and therefore a 0 steering command no longer keeps the vehicle driving straight. As you can see with the controller that has been described so far, the vehicle experiences a buildup of a lane offset, or a steady state error. One way to address this problem is to add yet another term called an integral term. This third measurement sums up the cross-track error to give an indication if we are spending more time on one side of the trajectory or the other. You can see that if we sum up the cross-track errors, we obviously spend more time on one side of the trajectory. The integral term we propose is then exactly this sum multiplied by a gain. Now, 3 gains will need to be tuned all at once, which can be quite difficult to do by hand. If the gain is too large, the controller can go unstable, because normal controller fluctuations will be exaggerated. If the gain is too small, it can take too long to respond to these dynamic changes. When the gain is just right, the controller will be able to quickly correct for the front end misalignment and return to its nominal performance. The combination of these 3 terms is then what is referred to in control theory as PID control. There are other more advanced controllers that can be used for self-driving cars, but they will all look similar to the one we have described in this video. There will always be some measurements made about the state of the vehicle, which are then compared to some desired vehicle trajectory to construct a steering angle that ultimately controls the car. Hopefully this gives some insight into the control strategies that can help make self-driving cars possible.
So does that kind of help visualize some things a little bit? So, yeah. So now I'm going to kind of tell you guys how you can make these things within code. Chances are what you'll be doing with whatever project you're on, any kind of control system that you have is probably just going to be written in software, but it is also possible to make it in the form of purely a mechanical system, purely an electrical system, purely, I don't think anybody has the opportunity to do a fluid system, but like, you know, there's a bunch of different ways to do it. So, basically, we care about our error. Basically what we have is, so this p-value right here at the very top, so this is just equal to, like, so all of this is pseudocode. You guys know what I mean by pseudocode, where it's like, it's not exactly code. Like if you just copy and paste this into like the Arduino IDE, it probably won't do something. You need to define a few things here and there. Like, for example, this thing, like, run thing based on PID output. Like, you'll make some function however you want. So here I just have a variable, I just have it called p, and I just have this equal to my command value minus my sensor value. That just gives me some difference. So for example, if my command value is at exactly 0, let's say I'm just talking like vertical height or something. My command value is here, but my sensor value is reading, I'm up here. If I take the command value minus my sensor value, so let's say that this is up at a height of 1, for example. That value of p, so my command value 0 minus my current position here, which is 1, that's going to be equal to -1. That then is basically telling me that I need to move -1 down to start getting back to where I'm at. Similar in the other direction. So if I'm at -1, if I take my current desired value minus my true position, so I have my current, or my desired position, 0 minus -1, I want to move positive up, basically. I'm trying to move to there. So then next, so that's just telling me my basic error, just nice and simple. Then I have this I term, this integral term. So what that is doing is that is over time, assuming I'm recording error over time. I'm just logging it to an SD card. I've got it logged to some sort of an array or a matrix or something where I'm just tracking this over time. I can basically look at my integral term is equal to like the previous integral value plus whatever the current error is times some change in time. So if I'm having something update every second, that dt value would be 1 second. If I'm updating this every millisecond, that's, you know, times 0.001 seconds or something. You can define your refresh rate however you want, but typically the faster your system, the smoother your operations can be as soon as everything is tuned properly. And then the derivative term, basically what you're going to have is if you're logging your error over time, you're going to look at what the current error is minus whatever the previous value of the error was. So, you know, I'm updating things over time. So for example, like earlier, if I'm trying to grab this marker at time 0, I'm at 2 feet away. 1 second in, I'm 1 foot away. 2 seconds in, I'm at 0. So if I were at kind of this position where I'm a foot away, my p at this value would be 1 foot away. That's my current error, but my previous error before this measurement was taken was 2 feet away. So I'd have this current value 1 foot minus 2 feet. So I have that quantity in parentheses and then divided by my dt, or my refresh rate, my refresh time really. So same exact value is up here. So it can be 1 second, it can be a millisecond, it can be a microsecond if you're fast enough. So that'll just get you 3 values that are telling you the current error, the rate of error, and the integral of the error. Then what you can do is each of these values, you can multiply them by some amount, some sort of coefficient. So here I have basically each of those 3 terms, they have their own little quantity and then they're just summed together. So for example here, I have my proportional error. It's just multiplied by some coefficient. I just have it called KP. You can change it however you want. KP, I just have that defined as some coefficient earlier in the code. It can be 1, it can be 2, it can be half, it can be like, it's gonna just take a lot of, you just test things out, and I'll talk about that later. Exact same deal with integral term and the derivative term. So you can basically, like over time as you're testing these things, you can, each of those 3 coefficients, KP, KI, and KD, you kind of just test one thing after another where it's like, all right, I'm gonna try a test where I'm gonna tune one of these gains up a little bit. These coefficients are called gains, if I haven't said that already. So you can kind of just tune things up and down until you get something that works. And I'll talk a little bit about tuning it later. And then that value, typically what you can do is, like with how you're scaling these things, you can have these numbers be whatever you want. So you can turn this error rate and just multiply it into something that you can then turn into a value just plug straight into here. So for example, run thing based on just whatever number gets spit out of this equation, you can use that to then control like a PWM signal, for example. You've got some duty cycle that's running from 0 to 100% that drives some motor, for example. You can, kind of similar how I was talking about like a potentiometer earlier, where you have some angle position, you're turning something from 0 degrees to 180 degrees or something. That's then changing something to a resistance that then is just scaling it up, basically. You can scale these values, these coefficients or gains, into whatever values you want. Then when you have something that's like some angle measurement recorded by a sensor, then that tells you, okay, I need to drive some motor on some other completely separate type of value or number system off of some output that I get from this equation. Does that kind of make sense to people? Any questions? I know I said a lot there. If you have questions. Clear? Alright, Gucci. So, response characteristics. So, kind of similar to like the car video we saw earlier. We kind of see, we have this car going and it'll kind of it can kind of trace its path, and it's kind of going from one kind of offline and goes and does another thing. You can see it kind of wiggle around. So if you go into control systems at all, you're going to see a lot of diagrams that look like this, where typically you have something starting at like 0, and then here it's trying to get up to a value of 1. Or you're going to have, something at one value, you're trying to get it to go to another thing. You're going from one lane of a road to another one, just changing values. So the behavior kind of showing how you move around and get to whatever your desired value is can be defined in a few different ways. And one of them is like how well the system is damped, and then another is looking at the natural frequency of the system. So here, looking at damping, you can kind of think of it as your restriction of motion. You're like, think of it like, has anybody here once driven like a really crappy car, or where like you have your car, you're driving, and then all of a sudden the power steering goes out, and you're trying to really grind the wheel over to actually try to make it turn? Think of it kind of like that. So you can have a system that is like over damped. That would be like your power steering goes out, you're really having to crank it, and it takes forever for your car to actually make a turn. It's a really slow response, so it's going to kind of gradually go up and then eventually get to some goal value that we have at the end over here. You can also have the reverse, where you have an undamped system or an underdamped system, where like an underdamped one, it's a little too loosey-goosey. It can shake around a little bit, so it can go and kind of go up a little bit. So it's like sometimes maybe like the first time that you're learning to drive, like you're going and making a turn, and it's like, oh, I'm turning a little bit too much. I need to kind of ease up a little bit and kind of go back out a little bit before turning too sharply into like a mailbox or a curb, or a squirrel, aka living curb, or whatever. Or you have an undamped system, which is just no damping at all. You're just going to completely shake around. There's no control. With that little airplane video at the start, undamped would be like a neutral dynamic stability system. It's just kind of just going. But then you could also have like a negatively damped system, or like a negatively negative dynamic stability. So then, rather than oscillating this kind of natural like periodic behavior, just go and keep increasing in amplitude until eventually you crash into the ground or reach escape velocity. Either way, you die. So that's kind of damping behavior. Natural frequency is basically, what do these oscillations look like? How fast or slow do these oscillations happen? So here we can see we've got a period of about, a little over 2, something. But you can scale that frequency a little bit, depending on like you can have systems that like are gonna have a really low natural frequency where it's gonna kind of gradually move into things, or you're gonna have like really, really high natural frequency stuff where it's just gonna shake around and jitter a ton. So damping, think of it like you can have like overdamped or underdamped. You can have an overdamped kid is going to be, you give them a handful of melatonin gummies and they just pass out on the floor. Or the other way, underdamped, where you just give them a bunch of sugar and they're going to be bouncing off the walls and give you a headache. Natural frequency. Have you guys heard of like constructive interference with waves at all? Okay. Well, you'll see in just a bit. So it's really good to make sure that whatever natural frequency that your system is at, make sure it's not in a way that can destructively affect your system. So for example, if you have some driving frequency coming in, like a disturbance or something, but then if your system naturally responds with that, it can then just increase, like where the waves basically keep building on each other and they'll just kind of shake itself apart. So one thing I've noticed, so Google decided to roll out one of their latest stupid policies in the last few weeks that apparently some videos aren't playing on Google Slides. Originally what this was going to be, so there was a really cute video of a cat that I found that basically it's a little cat, it climbs up on this little like box of raisins, but have you ever gotten where like if you're a little kid, you're climbing up on a ladder for the first time, like you're helping dad with Christmas lights or something, you get to the top and you kind of start shaking a little bit, or like if you're trying to balance, you kind of reach this point where you're just kind of naturally shaking side to side. Basically a kitten did that and it was really cute. But trying to demonstrate like a really underdamped response is like this, he's stable, but he's shaken. Really, really underdamped. Let's see if the next one works. Let's see. This one will work. So like a really overdamped response. So like everybody's seen Zootopia.
Nice to see you too.
So really, really slow responses.
That is what the DMV is like.
Mm-hmm.
I am doing just as well as I can.
Anyways, we don't have to.
What can I
But yeah.
do?
So an overdamped response. Let's see. This one, I do have. Let's see. If I bring this to here. So has anybody here heard of the Tacoma Narrows Bridge disaster? We got a couple people, a few people. For those of you that haven't, this is what happens when you let a system not get designed properly to account for certain driving disturbances that can happen. What happened here is literally just the wind blowing across a bridge was at just the right frequency to make the bridge actually wobble around and then completely collapse.
Opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
Yeah, steel and concrete and yeah.
Only at 35 mile an hour wind is blowing, but this apparently sets up a rhythmic swinging of the ridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Yeah. But yeah, so make sure you don't let something like that happen to your system. Let's see. Next thing. Also, has anybody here not seen? I think it's the third Pirates of the Caribbean movie where like they have to like roll the ship over. Not? All right, I'll pull up the clip. So there's this really cool clip where I won't go into the story of it, but basically for some reason, to get to like Davy Jones' locker or something, they have to flip the entire ship upside down, and then so what they start doing is they have everybody start rocking from like running from side to side on the ship, and starts rocking the thing side to side. So if this is something you actually need to do, then this is some way that, you know, utilizing that natural frequency with some driving frequency can actually be useful. So anyways, but yeah, if you haven't seen any of the Pirates of the Caribbean movies, definitely watch it. They're pretty good. At least the first three. Let's see. Go. All right. So, for the sake of time, I will not be talking about all of the other things that define the behavior of control system responses, but a handful of things that do often come up if you're looking at, like, or if you're investigating a control system, or your boss asks you to analyze, like, kind of the transient response of one of these things. You'll also have various characteristics, like you've got the rise time, like, which is considered basically the time that it takes to get from a position kind of down here up to here. It's the amount of time for that initial spike, that initial rise. You've also got your peak time, where it's like if you have some sort of oscillatory response kind of at the top, when does that maximum peak happen? You also have your settling time, like how long does it take to eventually get within some tolerance bound that's considered good enough. You also have your overshoot. That's like, how far up are you going? For example, your overshoot, if for like a thermal system, you want to make sure that your amount of overshoot on an engine, for example, the amount of extra temperature that gets generated while something is igniting isn't so much that it melts the engine, or if there's people around, it doesn't cook them, or something stupid. You also have your steady state error, kind of like that other video before, how like if you've got wind blowing something to the side, what is the amount of error that eventually gets generated, if any? Ideally, if you design your system right, it should go to zero, but doesn't always happen. And there's tons of other factors out there, but all of these can actually be calculated directly from damping and natural frequency characteristics. Those also are used for a thing called a transfer function, which I think I had mentioned on a slide at one point, but I didn't verbally say it. But that big ugly equation that comes out of the end of simplifying a big block diagram, that's used to generate a transfer function. That transfer function is basically what defines you have your input, some ugly math, output. That big ugly math in the middle is part of your transfer function, basically. turn this stuff into actually useful things. So just as a refresher, so we have our inputs, we have our outputs, we have our systems. So inputs, these can be commands. So like for those of you in C, if you have a control that you give on like your little joysticks or buttons that goes to your plane, telling you to maneuver some way, or also if you have things developed internally. So for example, RCS, you can tell, all right, I'm trying to command and get to some angle tolerance, or I'm trying to go to some angle position or something. You also want to be able to still record your disturbances. So this will be recorded by your sensors on all of your stuff. You'll have, for example, anything having to do with motion, you're probably going to have an IMU somewhere in your system. Something telling you acceleration in each axis. You've got rotation rates. You've got magnetic field vector stuff with your magnetometer. You can use those to trace your motion and see, like, all right, if I get a spike of moving to the side, probably hit a wind gust or something. Outputs, these are specific to each of your guys' projects, but you've got your responses and states. So, for example, for RCS, you've got your little cold gas thrusters. It's like you're telling one pair or another to fire for a certain amount of time, and then fire in the other way to stop, or something like that. For C, you're going to have all of your little control surfaces moving around, doing whatever. You can also have lights. You can have any kind of way that does something useful for your system. And then for your guys' systems, most of the stuff that you guys will be using, chances are you're going to have your process be housed on a microcontroller. So a Pico or a Teensy or whatever thing you're plugging in and programming with the Arduino IDE or VS Code, anything you're loading code onto is probably going to be where your main process is at. And then feedback systems, those are going to be your sensors reading data back into your microcontroller, which the microcontroller then has some kind of existing log or a stream of data that's just your historical positions over time. So when you guys are testing these things, they will not work the first time. I pretty much guarantee it. You turn that thing on, it's going to try to shake itself to death. It's going to look stupid. So there are a variety of different ways to tune these things, and they're all very specific to your application. So it's going to take a lot of, like, literally just kind of guess and check, or it's like, let's see what this does. Turn it on. Hopefully it doesn't kill anybody. Please don't. But make sure that when you are tuning these PID controllers or bang bang controllers or whatever other kind of controller you want to use, make sure you make each of those little tweaks one step at a time. So for example, if you're doing a 3D or not a 3D, a PID controller, you've got 3 different gains or values that you're trying to change over time. Just change one of them at a time. It can also be helpful to keep, like, you can keep 2 of them at 0 and then just change one until you get something useful. And then just change a second one, start doing that. Then change a third one, do stuff with that. Just make sure, or like what I would recommend, document the process as you're changing things, where it's like, all right, at this value, it just shook itself to death, and wanted to die. I changed it up, and it's like, okay, it's a little bit smoother. You know, just document it so that then inevitably, like, you know, it's 2 in the morning, you're coding this thing, and you're like, what did I do 20 minutes ago that really worked well, but I don't remember what those values were. Document it so that you can just look back and see what worked, just go back, and then, yeah. So, awesome, another video not working. I will say be careful for the first time, especially if you have anything that is trying to move very quickly, because you don't want to hurt yourself or damage the thing that you're working on. Go nice and slow with it. Don't do anything too janky. Just eventually get to a point where it's professionally janky. Originally what I had here, does anybody know who Michael Reeves is? So I'll show some clips. So he made a surgery robot, and I'm going to mute the audio because he's a little vulgar for a tutorial video, but he made a janky like surgery robot. So like he's got a whole gantry system. You can see he's early on in testing. He's got the thing, and it's moving, it's doing stuff, and it'll be like really exciting when you get the stuff running for the first time. It's moving, but you know it's not the final product yet. You want to be careful that you don't break anything. Eventually, he kind of has it fall off a table, I think. Let's see. But then, you know, later he gets it and it's a lot more developed, it's a lot better, it's ready for surgery, and let's see. Yeah, so then it's much more professional. It's a lot better. Everything's nice, safe, everything's fully controlled. Yeah.
And that doesn't look very safe.
It's pretty safe. Look at him. It's great. Yeah. If you haven't seen this video, highly recommend it. Like, does have some language, I will warn you, but it is really funny. He's got some really cool stuff. But let's see. Yeah. Let's see. All right. So, Bang Bang controller pseudocode. Very simple. If you have some command value that is something, you have some tolerance, which is then something smaller. Basically, tolerance meaning, you know, say I want to be around a value of 1 for something. My tolerance can be like 0.1, which tells me, all right, I need to have my thing be within 0.1 of 1, meaning like I can be anywhere between a range of like 0.9 to 1.1. Like that's a good enough level for me to where I don't need to do anything. And then while I'm going through some loop, I've got my sensor. It's reading some sensor value. It tells me a position. It tells me some motion rate. It tells me something. And then if that sensor value is then, and if it's less than, like the difference between like my command value and a tolerance, so it's like if I'm trying to move something at an angle, if my angle is, let's say I'm trying to move something to 90 degrees, for example. Let's say this is 90 degrees, this is 0, this is 180 or something. Let's say I'm there. If I have my command value, which is 90, and if my sensor value, which is like down here at 45, if it is less than that command value minus some tolerance, meaning if I'm at 90 degrees, let's say I have a tolerance of 10 degrees. If I am less than 80 degrees, so 90 minus 10 degrees, if I'm below 80 degrees, do something. So just like go up. So here I'd be moving the thing up until I get to some level. And then same way the other way, if I have like some angle, say I'm at like 180 degrees, and if I am greater than my command value plus a tolerance, so say 90 degrees plus 10 degrees of tolerance, so 100 degrees, if I'm greater than that, then move the system to go down and do that. If I'm doing anything else, if I'm in any other state other than these two, that basically means I am within the tolerance bound of the system, then just do nothing. That's considered I'm in a good enough position, I don't need to do anything. Any questions with that at all? Anything perfectly good? All right. Similar deal here, similar style here. So how I mentioned some of the pseudocode for PID controller earlier. So we can have some command value is something. I have some initial variables for time up there. So I have like time initially is going to be 0. Then I have like my previous time is 0, just initializing them. Eventually that'll be updated each time. And then I have some variables, KP, KI, and KD, which are just like gain 1, gain 2, gain 3. These would just be numbers in your guys' case. We also then have some variables get initialized. We have P, which is our just proportional error. It's just going to be something. And then our previous error, we have our just integral term, initializing all of those as 0. Those are going to get filled up later. And then we run some loop. Our time is then going to get updated. Say we have some function called like just get time. I know like in Arduino you can use like the millis or the micros function that just tells you how many milliseconds or microseconds have passed since the system turned on. You're just updating what time is it basically. That's all I'm doing. Then I have a variable called dt. That is just a difference in time. That is just the current time minus the previous time. So over time, as this is all cycling through, there's a little thing down here that updates the time. But let's say a previous cycle, the time was 1 second. And then at the next cycle, it was 2 seconds. Now I have my dt being my current time, which is 2 seconds, minus my previous time, which was 1 second. dt is then just the answer to that 1 second, just the difference between the two. Really, this would probably be a much smaller thing for all of your systems, doing microseconds, milliseconds. Then you're going to have sensor value get updated. You're going to have some function reading your sensor. You're going to have something telling you a position or an orientation, something like that. And then you're going to update your P, I, and D values exactly the same as before. You're going to generate some sort of output from those error values and your gains associated with them, just like before. You're going to run some function based off of that value, just like before, and then you're just going to update some things before the next cycle. So you're going to update that error, and I forgot to color code this, crap. But the previous value is now going to get updated to be the current value. So then by the time you loop back around and you get a new value for P, then that's going to be some other new value, and you're able to reference what P was in this past cycle. So you have that, and then you do a very similar thing with the time. So you have time previous is equal to the current time. Then when it loops back around and gets referenced again, we have a new time and the previous time from the previous cycle. Any questions on any of that? And also, these slides are available on like Canvas, or they will be if they're not right now. And then you can copy and paste this however you want. So, when you're tuning these things, like I mentioned, there's a whole bunch of ways depending on what your system is. There's some things where it's like, all right, so if you have your thing, you change one value to be something, and then you wait until your oscillations are at some number of period or like some rate or something, and then you have some other damping. There's a bunch of different goofy ways out there. It's kind of one of those like, kind of think about it like, you know how with like a system of equations you'll have like 3 equations, 3 unknowns, and you can very easily determine which things go best. Here it's not like you have 3 equations. You just have 3 unknowns, and you just kind of guess until you get something good enough. There are processes that are like, all right, here's a really good way that narrows things down to like a really good performance level for different applications, but chances are for 2 months, what you guys are probably going to do is just wing it. But you can look up a bunch of different resources online, just like how to tune a PID controller, and see what you find, see if there's anything relevant to what you guys have. Yeah, I will say, the more you F around, the more you will find out. So if you haven't seen that graph before, then now you have. Also, control systems, they are not purely only a software thing. They can also be in the form of a bunch of different other forms. So you can have them as like mechanical systems, electrical systems, you can have them as a whole bunch of different things. But basically, as long as you have a system with components that are defined by proportional, derivative, and integral behaviors, you can make control system equations for them and make analogs for them in other forms. So you can make a circuit equivalent of a mechanical system, or a fluid equivalent of a thermal system, or there's some different things. The equations right here, these are used to define what's called a spring mass damper system. This is when you ever enter a control systems class, or you might get into, I don't know if you guys have vibration related classes that are part of your plan. I'm not sure. I took a vibrations class at my school, but you'll see one of these eventually. You will use it a lot for so many freaking things. Basically, how the system is defined, we have just a mass right here. It's just an object, and then that mass's motion is then affected by a spring and a damper. A spring, y'all know what a spring is. A damper, does everybody know what a damper is? Does anybody not know what a damper
Like a
is?
pneumatic piston or something like that. It's set resistance, basically.
Mm-hmm. So what's important to know is that the way that we can characterize the motion of all of this can be defined by this equation right here, or well, this equation and different forms of it. Basically, this is composed of multiple forces. The total forces acting on the mass basically can be determined in a component specific to just the mass object itself. So we have this equation right here, which is the mass times an acceleration, or like x double dot, or second derivative of position, just acceleration. And so in one case, that could just be acceleration due to gravity, 9.81 meters per second, or 32.2 feet per second if you really want to use freedom units. And then the force acting by the damper is defined by some constant times the velocity of the system. So if you have imagine you've got your hand in like molasses or something. If your hand is just, sitting in a pool of molasses, it's not exerting a force on you, but as soon as you try to push one way or another, the faster it's moving, the more force it's going to apply. Similar also to the force of drag on something moving through the air. The faster you're going, the higher that force is going to be. And then you have the spring, which the force of that is just, some spring constant times the current position. And so each of these forces, you can just sum them all together, and then you're going to be left with an equation like this, where we have some force function as a force over time is just equal to some mass times acceleration, some damper or some damping coefficient times your velocity times a spring constant times your position. And then this is just that equation, just with dx, dt stuff for those. There's also this thing called the Laplace transform. I won't talk about how to go from this to this. Look it up on your own time. It can make, it might sound complicated, but basically what it is that here you have functions of time. This is, or like a Laplace transform is, rather than being in like the time domain, it's in what's called the frequency domain. It's kind of like this other way of looking at things. Like it's kind of weird, but if you transform something from like the time domain into the frequency domain, it lets you do some math that's a lot simpler and then revert back to a time domain function later, rather than taking another like 30 extra steps for something that's some equation in the time domain. Is anybody here in like differential equations, or has taken it? Does anybody not know what differential equations are? Or
We're gonna love it.
I'll just say I hated my differential equations class when I took it, but like you'll end up with functions that look like this, and you have some function as a function of time. It's also defined as equal to some function times the second derivative of it, and the derivative of it, and the function itself. It's like, what the heck does this function actually be?
So what this kind of mass is?
A little bit, yeah. So it's the like, if I wanted to have, if I wanted to get what this actually is, but not in terms of like derivatives of itself and everything, it's what is the function just by itself. Differential equations help you get what that function actually is. What it, like, if you were to just plug it into like Desmos or something, or some graphing calculator, just what would it look like? So, with that, in differential equations, you'll learn how to take, or at least if the class is taught well, you should learn how to take something from like the time domain and then transfer it, or do like a Laplace transform on it to turn it into the frequency domain. You'll get simpler equations like this that let you do a little bit simpler math. So then with this, you can then basically, rather than treating things as derivatives, you can just treat things as exponents, which then it's just like a quadratic equation basically. You do some stuff, you figure out what s is equal to, and then you can use that to then go back and you do some other things. But that's a whole other thing. I'd recommend looking it up on your own time. If I were here teaching how to do that math in this class, we wouldn't be out of here until like next week. So some of this behavior, just showing spring, damper, and mass components, and just some of the associated equations with them. So I showed you on the previous slide basically force as a function of displacement, or basically position of that mass as a function of time. But see ya. But what you can also do is, if you just integrate each of these terms, you'll get this column of equations right here, which might look a little familiar to something we talked about earlier. We have a proportional component, we have an integral component, and we have a derivative component. PID control, or PID components. So you can have things that look like this, that, you know, you have some type of system, it's defined by some sort of equation, you can have some sort of a diagram, and as soon as you have these kinds of governing equations for something, then you can start saying, all right, say I want to have a, say an electrical equivalent of a mechanical system. In my electric system, like for like spring mass damper, I have a few different components here that the behavior of those is analogous to this, and I'll explain kind of what some of those things are. So there's, on each of these things, with the exception of like thermal's kind of weird, but each one of those systems can be defined as a combination of integral, proportional, and derivative components. There's also kind of an input source, which typically is associated with whatever your, like, for example, a mechanical system, the thing you actually care about is like the position of the mass. So you've got like things acting on the mass part, so in this case, force, for that. An electrical system, what you're really caring about is like the voltage across some component. So the electrical equivalent of a mechanical spring is a capacitor. The electrical equivalent of a mechanical damper is a resistor. The electrical equivalent of a mass in a mechanical system is an inductor. So a capacitor, basically it accumulates voltage, it sucks things in, it kind of holds on to charge, and then kind of dissipates it out once it's able to. A resistor, it resists flow of energy through a circuit. An inductor's just weird. I'm probably going to give a bad explanation for it, so I'm just not going to. Basically, it makes electric fields, they kind of feed in on themselves a little bit. You can do them for, a lot of like power systems use them for things, but I'm not an electrical engineer. Question?
I think it's magnetic fields with inductors, right?
Technically, yes and yes. Like, electric fields and magnetic fields are like, yeah. Like, right hand rule, you got like, by the way, if you don't know right hand rule yet, this is the international gang sign of engineers that have, like, you just, if you see somebody going like this, you know what they're doing. Like, yeah, like it, that gets into weird, like, electrophysics stuff, like electric fields and magnetic fields. Anytime you have one, you always have the other. Also, it's weird, but yeah. Hydraulic systems, the equivalent of like a capacitor would be, you can have like a tank or a bladder or a membrane. It's kind of, you know, it's accumulating liquid on the inside and then dissipating it out when it gets the chance. For a resistor or a damper, you also have a thing like you have a filter or some way of constricting a pipe that's resisting flow. And then for like the derivative components of like a mass or an inductor, you have like a turbine or a water wheel for a hydraulic system. You have some amount of pressure, or like you've got water flowing through something, it's turning something, and then that then goes and powers something else or drives something else. Thermal systems, if you guys ever take a class called like heat transfer or heat and mass transfer, especially any mechanical or aero people, just take it. From what I can tell, it's not a required class, just take it. That should be a required class for any mechanical or aero engineer.
It's always been
It,
required for mechanical.
okay. I didn't know, because like there's some people that like I've worked with here that like they're in grad school and they did undergrad here and they never took heat transfer. It's like, that's concerning. And you're working on a rocket engine right now? Yeah, I don't feel comfortable with that. But yeah, so for like a capacitor, you have a conductive mass. It's sucking in energy. It's sucking in heat. It's think of a rock sitting out in the sun. The sun's just beaming in. It's beaming heat at it, and the rock is just sitting there. It's getting a bunch of heat, and then, you know, if you put a shade over it, that heat doesn't just disappear. There's still a bunch of heat stored in that rock. So if you touch it, it might burn you, depending on if you live in Arizona or not. Resistor, you have insulation. So if you take heat transfer classes, you'll learn about these things called like thermal circuits. You can literally do like, at least you can do a lot of like heat transfer math and everything literally by translating that physical system into a circuit, and the math is a lot easier. So insulation is the equivalent of a resistor. And then in software, this is just the stuff I mentioned earlier, so you can kind of define it however you want, but it's typically all revolving around error. So all of these, you know, if you know the math for one system, you can then translate that math into any of these other systems if you want. So you can make analogs of each other. So rather than making some big, fancy, expensive, dangerous mechanical system, if you know how each of those parts would be designed in the real world, you can then just make a really small circuit that you just put on a breadboard with a few resistors, capacitors, inductors, and everything. And if you're trying to look at the forces acting on something, you can basically plug a thing in with a similar voltage source as what the forces would be on some mechanical system, and then you hook up some sort of a meter to the end of the circuit that then looks at the output behavior. It will exactly match the same type of behavior if you accounted for everything properly. So you can make all these different analogs. You can do like, let's see, if I go back, any of these systems, you can make an analog of the other with any of the others. And I'm pretty sure there's also a handful of other types of like systems or analogs, but these are the ones that are at least somewhat relevant to you guys. So a lot of early computers actually were made for similar applications like this. You have some big, ugly, complicated thing you're trying to simulate, just make it on a circuit, simulate it. It's a lot cheaper, a lot easier, a lot safer oftentimes. So yeah, right at the end, you can go home soon. I will say, this stuff is complicated. This is hard. There are loads of tutorials on the internet about, like, if you look up how to make a PID controller, you're gonna find hundreds, if not thousands, of results on, okay, you have an Arduino, you have some motor, you're trying to control it, you're trying to do something. There's loads of stuff for that. Also, if any of you guys want, I do have, I have like my old controls textbook that I can show you guys at some point. But also, like, if you just look up how to do control systems, you'll find loads of stuff out there. It's a very huge field. Like, there's one guy that, that little graph I showed earlier where it's like something curving up and then trying to get to some goal value. His entire PhD dissertation that he's doing is just on that little initial curve behavior, but it's for the startup of like a nuclear thermal propulsion system. Like, just that little behavior, like, just loads of stuff with it if you want. Like, he's, at this point, I think he spent at least 2 years on it, and going on, I think, at least another third or fourth year. I'm not sure. It's been a while since I talked to him. Like, there's a lot. But once you start understanding how some of these things work, you can start, like, assuming you have a decent physics background also, you can start learning how all of these things work. Not just technological stuff, but also you're thinking biological things as well. Pretty much anything of any level of complexity in the world has a control system down at the core of it. And if you know how they work, it helps you learn a lot of things very, very quickly. You can just kind of look at something and you're like, well, I know how that works. It's kind of cool. If you want to look at other things, some other things that I would recommend checking out are these things. I'm not going to read them all out, but yeah, these are like, if you go into a control systems textbook, there's entire chapters on just individual one of these things. Like transfer functions, probably going to be at least like 3 or 4 chapters in a textbook talking about just that. That's those like those big equations that define your system after you simplify a block diagram or something. There's a few other things that are for like determining the stability of your system, different, diagrams of things where it's, you get some like, I'll say root locus stuff. If you get, or like just look up like root locus charts or graphs, they get weird. But yeah. Anyways, it is hard. I get it. Like I almost like, this was one of those classes that I took, like, getting farther along in my degree. It's like, do I really want to do this? This sucks. But, like in that class, like everything kind of sucked all the way up until like about like a week or 2 before the final exam. I, was, grinding away, working on this stuff, and then everything clicked. And it's like, I get it. And it was like a beautiful thing, like a totally geek moment, but like everything starts clicking, everything makes sense. It's like, okay, now I understand how to actually use this. And since then, like controls has been some component of pretty much everything I've worked on since. They're very important. Once you understand them, you understand how pretty much everything else in the world works. And it's at least on Earth, like man-made society, I mean. But like, yeah. So I've done what I can to try to simplify and distill a lot of super ugly control systems theory into something that hopefully is at least somewhat approachable by y'all. But yeah, there is loads of other material out there to look at if you want. But hopefully this is at least somewhat helpful. Are you at least at a point where you're like, all right, I don't know something, but you don't know what you, or like, are you at least at a point where it's like, if you don't know something, you know what to start looking for, basically? Does everybody kind of see how some of this control systems theory can apply to each of your projects, whether it be like C with like, controlling control surfaces, or RCS with shaking things around, Rover with trying to get to some position or speed or move an arm around. There's the rocket one. Rocket has altitude stuff. There's some stuff in there. What's the last one I'm missing? CanSat. Probably some altitude stuff as well. Yeah. there's some level of controls in all of these things, and if you have questions on any of this, ask your mentors, and they will help, or at least should hopefully help put you in the right direction. And if they don't know, then feel free to ask me. I can try to help give some input. So, any questions?